All right, good morning on-ramps classes. So this is our second day for hypothesis testing for 4.2, and we want to talk about a few things that can occur when we do hypothesis testing and what happens when either we don't get the results that we want or we misrepresent the results that we have. So there's two types of errors that can occur during hypothesis testing when the statistician does not evaluate his null hypothesis and or alternative hypothesis correctly. So one of the first types of errors that we can get is a type 1 error. So you can see here in our chart, I've given you a chart to see when your null hypothesis is actually true and you reject it, then when you're supposed to accept it, or when we say do not reject. So I'm going to put here, typically our wording is do not reject when it's in that, pink area between your confidence interval. So if it's supposed to be a correct decision, but you actually reject it, that's a type 1 error. So that's also known as a false positive. And you have probably heard of these in like medical testing, right? If you get a medical test done and it's positive, but it's actually negative, that's called a false positive. So it's rejecting the null hypothesis that is actually true. So I have a little joke down here of, here's an example of a type 1 error. It's a false positive, so telling this man here that you're pregnant when in fact he's actually not. And he's obviously not. So a type 2 error is when your alternative hypothesis is true, except that you except you do not reject the null hypothesis. So when you're supposed to reject, but in fact, you accept when you should not. So this is called a false negative. So the definition here is accepting a null hypothesis that is actually false. So another example here of a type 2 error, your false negative, when the doctor here is telling this woman who is obviously pregnant that she is not pregnant. So that's a false negative, when in fact you should have accepted the null hypothesis, right? All right, so each of the errors occurs. So we have a couple of things here. We've talked about alpha before. Alpha is the probability of a type 1 error. So think probability is between 0 and 1, or 0% and 100%. And we'll talk a little bit about that more after the break. And then we have beta is the probability of a type 2 error. It's the probability of not rejecting the null hypothesis when the null hypothesis is false. So here, alpha and beta should be as small as possible because they're probabilities of error. They're rarely 0. So here, the power of the test is 1 minus beta. Ideally, we want that, go away. We want a higher power that is as close to 1 as possible. So increasing the sample size can increase the power of the test. So the following are examples of type 1 and type 2 errors, and we'll talk about p-value, and we'll get into like actually knowing that number on the back of our notes here. So if it's still fuzzy, that's okay. So here's one example. Here's our type 1 error. Frank thinks that his rock climbing equipment may not be safe when in fact it really is safe. Here's our type 2 error. Frank thinks that his rock climbing equipment may be safe when in fact it is not safe. So he should have rejected it, but he actually accepted it. So alpha alpha is the probability that Frank thinks his rock climbing equipment may not be safe when in fact it really is. And beta is the probability that Frank thinks his rock climbing equipment may be safe when in fact it is not safe. So notice in this case that the error with the greater consequence is type 2 error, because if his rock climbing if he thinks his rock climbing equipment is safe, but it is not, it could be fatal for him, right? So that's not good. We want to make sure that our testing is correct. So here's our null hypothesis for this example. The victim of an automobile accident is alive when he arrives at the emergency room of a hospital. So you can pause and try this. So our type 1 error, a false positive, right, is that the emergency crew thinks the victim is dead when, in fact, he is alive. So the victim is alive when he arrives at the emergency room of the hospital. So false. Positive would be that the emergency crew thinks he is dead when in fact he is alive, when the null hypothesis is true, right? But we should have accepted it, but we did not. We rejected it. All right, the type 2 error is the emergency. You can try this too. Crew thinks okay, so the type 2 error, the false negative, when it should in fact be, you should reject the null hypothesis. The emergency crew thinks the victim is alive when in fact he is dead. So those are a little overview of type 1 and type 2 error. Let's flip it to the back and we'll talk about a little bit more about this alpha level and p-value. So alpha level we talked about was the probability. So it's a significance level. If we're on-ramps, we call it a significance level that tells us what area in the tails of our distribution we consider our rejection region. So we've talked about this in our confidence interval is 95%. So this is the alpha level, that 0.05, that tells us when we need to consider it our rejection region. So so again, we are going to use that 0.05 area. So it's alpha level and p-value kind of go together because the p-value is the area beyond our t-statistic toward the tails, and it's a probability. So the p-value is considered a probability that measures the strength of evidence against our null hypothesis. So we're going to say the probability, and remember in probability, we can say it as a proportion, right? A decimal value, but generally we say it as a percentile or a percentage. So probability that measures the strength So I'm going to write this against. So this is against null hypothesis. So when your p-value is low, the lower your p-value is, the more evidence you have against the null hypothesis. So if your p-value is less than your significance level, our alpha level 0.05. So if your p-value is less than 0.05, then we know to reject our null hypothesis. So if you want to ask me about a little joke about this, you can. I won't say it on camera. But so as your p-value gets lower, so think this is 5%, right? So if it gets lower than 5%, then we're going to reject the null hypothesis. So this is just the strength of evidence against the null hypothesis. So let's look at an example. A pharmacist is supposed to dispense 10.2 ounces of penicillin for a standard 10-day treatment. The lead pharmacist conducted an experiment to determine if her staff was meeting the requirement. Here are the results for her test. So here is our null hypothesis. Our null hypothesis is that the average is 10.2 ounces, right? Our alternative hypothesis is that they're not equal, right? So we want to equal 10.2 ounces to see if our samples are actually in the range that we need them to be. And then our t value, so remember this is our t critical, or t statistic, sorry, t statistic. That's our formula that we learned about last time, our t statistic. So this is actually where our 10.2 would fall on the region that we built. And then our p-value is 0.00034. Well, that seems very small, right? So remember, the smaller that it gets, the more evidence against. So I'm going to write that here. So it's not looking good so far just by looking at these numbers, right? But let's determine exactly what happened. So he analyzed 51 samples and the sample mean was 9.7. Can you determine the standard deviation of the sample? Well, yes, we can. Even though we don't have the standard deviation, we can work backwards, right? So think about our t statistic formula, right? Our t statistic formula was x bar minus the null hypothesis mean divided by standard error. And standard error was the standard deviation divided by the square root of n. So let's plug in all the information that we do know, and then we'll find out what that standard deviation is. We know that our t statistic is negative 5.89. We know that our x bar is 9.7. We know that our null hypothesis mean is, or our claimed value is 10.2. We don't know our standard deviation, so I'm going to call that S. And then we do know our sample size is 51. So I'm going to think about it like this, and I'm going to cross multiply here. So we have negative 5.89 times S divided by the square root of 51 equals 9.7 minus 10.2, which is negative 0.5. So now I'm going to multiply both sides by the square root of square root of 51, or you can think about it again as cross multiplying. So we have negative 5.89s equals negative 3.57, and you can say 0.7 or leave it like that, whatever. And then we'll divide and we get x equals 0.606. So our standard deviation, or our sample standard deviation, is 0.606. So that's our answer for that one. So degrees of freedom for the test, remember degrees of freedom are n minus 1. So if our sample size was 51, it's 51 minus 1. So our degrees of freedom are 50. And then how do we interpret the p-value for this test? So let's think about this. If it's degrees of freedom are 50, then my t critical value, let me get my t chart out here. My t critical value is whatever's closest to 50. So let's say it's 2, right? So if our t critical value is 2, look at our t statistic. It's negative 5.89. So that's saying that if this is my 0, right, my mean, and it's 2, so +2 and -2, where does this t statistic fall? It falls at negative 5.89. That's way down here. So think about that. We know that it's in our rejection region, but we also know that it's very far into our rejection region because the percentage is this 0.00034. If we change that to a percentage by moving the decimal twice, it's still 0.034%. And it has to be anywhere less than 5, right? So that means that it's a very, very strong possibility that the sample mean is not what it should be, right? Because it's supposed to be 10.2 and it's very far away from that. So far away that we cannot blame it on sampling error, that there's actually an issue with what's going on in his pharmacy, right? So what does this mean? We can interpret it like this. There is only a 0.034% chance that the sample mean, sorry, I'm writing into other things, would be observed if the pharmacists are following regulations. So that's a very low probability that the pharmacists are doing what they're supposed to be doing with penicillin. So good thing the lead pharmacist went through and did that study. So please complete 4, 5, and 6. Show me when you have finished that so I can check off on that. So here's the exact T critical value for you, and I've kind of already given you a little graph of that. So you should be able to do the rest on your own and then check with me.